lecture 21. I'll give this lecture on random CNF logons for cunning planes, for the cunning planes process. All right, so we have seen cunning planes before, in particular last lecture, but let me just remind you what cunning planes is. Right, so cunning planes is a proof system that operates over linear integer inequalities. So like you have to form AI xi is larger than some A, and I always assume that the AI is in capital A are integer. Anything is unclear, just ask me during the lecture. And then we have some syntactic derivations, right? Syntactic derivation rules. First, we have the axiom rules or the Boolean axiom rules, which are very boring in a sense that you can just always derive that xi is larger than 0, and we can always derive that minus xi is larger than -1, or xi is larger, is at most 1. All right, then we have the addition rule, which just allows us to sum two linear equations, right? If we have the sum of the AI xi larger than A, and we have the sum of BI xi is larger than B, then we can derive the sum.
Sorry, this is certainly on the very small side.
Can we increase the font size a little bit?
I'm really bad at this. I can try.
Okay.
I'm not good at that. So, but AI plus BI times xi is larger than A plus B. So it's just a linear combination. Then we have multiplication, or whatever. Multiplication. Anyway, just come to Copenhagen if you want to see. So we have the sum of the AI xi is larger than A, and then we can derive the sum of C times AI xi is larger than C times A. And again, everything has to be integer. So this makes sense because we're over integer linear inequalities. And finally, the only interesting rule is division, which allows you to divide, but because we are over 0, 1 or integer points xi, we can round the right-hand side up. So if we have something like sum over I of ci ai larger than A, and we have the xi up here, and we have the common divider ci for the coefficients, then we can derive the sum of the ai xi larger than A divided by C, something like this. And round it up, that's the whole point, right? Because we are over the integer for 0, 1. So this is cunning planes. I hope this is not a surprise. And the other object that we want to look at is a random k-CNF. Keep this, let me write it here. So random k-CNF. Okay, what do I mean by this? Well, we have like some clauses, C1 up to Cn. We have variables, x1 up to xn. And we're going to choose every clause to be a k, like over k variables uniformly at random. So what I mean, like we choose a k subset of the variables uniformly at random. Okay? Like from any k subset, you choose one uniformly at random. Right? And then, every clause ci will be just a OR of variables xi, and then again, we choose the negations uniformly at random. Again, these are uniform. Okay? So good. So far, so good. That's a random k-CNF. And if we know that we sample enough clauses, at some point we'll become unsatisfiable, right? Because we just have too many constraints and then we're unsatisfied. And actually, like if n is larger than, I wrote it out, nn2 times 2 to the k times n. We have this many constraints, then we're unsatisfiable with high probability. And there's again the threshold behavior, and you can study where this exactly is. Not so interesting for us, but it's an interesting question, but not important for us. But yeah, if we are large enough, we're unsatisfiable. That's all we need to know. Good. So what are we going to prove? We're going to prove the following theorem. We're going to prove the following theorem, namely that if you sample random k-CNF with k logarithmic, then these formulas are hard for cunning planes. Okay. What are we saying? We're saying that if we sample our k-CNF phi from this distribution that I explained over here, and I'll denote it by f n, and then I'll parameterize it a bit funny. It will become clear why later on. So if I sample phi from this random k-CNF where I have n constraints over 2n variables, and each constraint is of size 2k, where we choose n to be something like theta of n, right? Large enough so that we're unsatisfiable, because that's another interesting case. Sorry, n tends to 2k, I guess. And we have k is larger than some constant times log n, then semantic cunning planes requires size 2 to the omega n, to refute phi. Okay, let me parse this just once again. If you sample phi as a random 2k CNF over 2n variables, or n large enough, and k to be some large constant times log n, then semantic cutting planes require size 2 to omega n to refute phi. What I mean by semantic cutting planes, right? I'm like here, I spelled out one possible definition for syntactic derivation rules, right? But you could imagine others like saturation or other rules. And what we're saying now in semantic cutting planes is just that you can derive any linear inequality as long as it's implied by your assumptions. Okay. So what I'm saying in semantic cutting planes, I don't know where here. It's here. So if you have semantic cutting planes, we can derive anything, the sum of ci xi larger than capital C, right? From any like ai xi larger than a, and sum of bi xi larger than b, as long as this inequality is implied by these two over the Boolean assignments. Okay, so you're allowed to derive anything you want in a single step as long as it's implied. The only constraint is that you can only use two assumptions to actually derive. Okay, you cannot take the whole formula and like somehow in one step derive contradiction. You can only take two things to derive. Other consequences.
Sorry, you mean the other way around, right? Like,
I think you just switch the order of premises and conclusion.
yeah.
Yeah, this was top down. Well, yeah.
Okay, just
Here. Sure. Let me just write it correctly. So we have the sum of ai xi larger than a, and sum of bi xi larger than b. We can derive ci xi larger than b. Okay, and we may derive anything for our premises that is logically implied over Boolean assignments. All right, and we actually know that semantic cutting planes, not so surprising, is stronger than syntactic cutting planes. Is a result by Hrubeš and Robere from, I don't know, before my time. All right, good. So we have stated our theorem that we want to prove. And now let's just take quickly a step back and think about what we have seen so far about cutting planes. So what have we seen? We have basically seen one lower bound method, right, in the previous lecture. So right, if you want to prove CP lower bounds, then we know that we can do interpolation. But seemingly interpolation somehow only applies to formulas where you have an explicit split of your variables into like two sets x, y, and another set z here, which is somehow shared. And you want to, given an assignment in the z variables, you want to tell whether the formula with the x variables, x and z variables is unsatisfied, or whether the formula with the z and y variables is unsatisfied. So it seems, at least at first sight, that interpolation is not really what you want to use to prove random CNF lower bound. Okay. All right. And then another thing is that we have no good width measure. Measure for cutting planes. So how can we see this? Well, the normal pigeonhole principle is easy. So pigeonhole principle is easy for cutting planes by just summing the constraints on the left side and on the right side. But it still requires like inequalities over many variables. That's somehow the natural width measure that you can have. So right, but still it requires a large inequalities. And what I mean by this is really like over many variables. Okay? And this is just by a normal width argument, you can argue this. So this is kind of saying that to prove size lower bounds, it's not really useful to lower bound the width of a complex refutation. Okay. And then last but not least, what else we have seen is that we have seen restriction arguments, right? But I mean, if you take a linear inequality, CIXI larger than A, and you hit it by some restriction saying xj is equal to, say, 1, then not much is happening, right? You're not really killing any terms or anything useful. Maybe you erase some variable, maybe the xj variable, and you change this constant term. But under restrictions, not much happens. Okay. Okay, so the only method that seems to work is really interpolation. And this is also how this theorem was initially proved. Okay, so even though random CNFs don't have this natural split of formulas that you can prove or use interpolation for, you can actually kind of force a split of variables on these random CNFs and then show that you can still use interpolation in some way. Okay. I should say that this was initially done by Hrubeš and Pudlák and independently by Fleming, Pankratov, Pitassi, and Robere. And we will look at a proof due to Sokolov. And we strengthened this theorem slightly by proving slightly stronger lower bounds, who actually took the monotone real circuit lower bound and somehow incorporated it directly into the lower bound argument so that we don't have an argument split into two parts, namely arguing that given a small proof, you get a small monotone real circuit, and then arguing that you actually have a monotone real circuit lower bound, but like somehow all these arguments mushed together into one, and it's actually much cleaner. And we basically end up with a bottleneck counting argument. Okay, so our proof today will be based on interpolation. You will not explicitly see interpolation. The intuition clearly comes from there, but ultimately it's like a bottleneck, as we have seen for the click point. All right. Good. Okay. So, all right. So, but first, before I start with the proof, I need to somehow explain to you how we enforce this split of variables on a random CNF. And this is why I parameterize this a bit funny, namely like 2n variables and of width 2k, so that I can do this split naturally. So what we'll prove today will actually not prove exactly this statement, but we'll prove a closely related statement. And then we will sample our random CNFs a bit different. So now what we'll do is we'll have two variable sets, one variable set x and one variable set y. And you should really think of we have these two sets because originally we wanted to do interpolation. And now every constraint is going to sample a random k subset from X and a random k subset from Y. Okay. Now, instead of like having one set of variables and choosing a 2k set uniformly at random, we're going to pick first k variables from this X subset and then k variables from this Y subset. And each, like both of the size of these variable sets is equal to m. Okay. Right. And I'll call now this way of sampling a CNF. I'll denote by this B of M N K. And instead of proving this statement for F, we'll actually prove this statement for B of M and K. This is really just to make the proof cleaner. If you want to prove the general case, you're also going to prove it basically for this version, but then you have to argue that such a split actually exists and everything is fine. Something I don't want to do. It's boring and it's just annoying calculations to check that this works. But basically, like from this model, which it might seem a bit artificial at first sight, you can actually get this natural model that I outlined. Okay, like the door rounds. Yeah, whatever. Oh, you understand whatever.
So basically what you're saying, if we do a sample of random k-CNF formula and then very unbalanced clauses will basically just restrict some variables and clean things up and remove them somehow, and then argue that what is left is kind of balanced.
Yeah.
Something along
you
these
pick a
lines.
random partition and then you argue everything's fine. And I mean, keep it this problem. There are some assignments that are not fine, but you're just fine. All right. Okay, so, and maybe not so surprising, what we will rely on is expansion of this graph. So let me just quickly state what expansion we will rely on. But maybe somewhere where I can keep it. So let me just state here lemma that if we sample a graph like this, then I can call this graph up here G sub X, and this graph here, G sub Y, right? G sub Y. And all I'm claiming is that both these graphs are excellent expanders if we choose these subsets uniformly random. Okay. So what am I saying? So for K equals theta of log n, and n the most order of n times 2 to the k. And there is a constant C such that such that Gx and Gy are C times n over k, k over 2 expanders. Okay, so let me quickly parse this. So for our setting of parameters, we choose k to be log n, and m at most n times 2 to the k. Then there is some constant c larger 0. It's unreadable. Sorry, constant c larger 0, such that gx and gy are both n over k, k over 2 expanders. What I mean by this, so what is this expander? We say that any subset of this size has at least k over 2 times the set size many neighbors on the x set or the y set. Okay, so let me just go an S K C expander satisfies that any subset S of size at most, so for all S of size at most S, satisfies that the neighborhood of S is at least C times size of S, and the left degrees are of size K. Okay, and the degree are equals to K. I hope it's fine if I stated somewhat wrong. And all I'm saying is that if you look at any subset here on the left-hand side, size n over k, then we have k over 2 times the set size of n neighbors in either x and y, in x and y. Okay. Good. And so, okay. So now we have introduced the split into x and y. And now I kind of want to view inequalities as some objects related to sets x and y. And motivated by communication complexity, we're going to look at a matrix M. So this is our matrix M, which is indexed by assignments alpha, where alpha is in 0, 1 to the x, and assignments beta, where beta is in 0, 1 to the y. Okay, so we can look at this a matrix like this. And now I want to understand what an inequality looks like in this matrix, or what combinatorial, what does it correspond to as a combinatorial object. If you look at clauses, by the way, this is a combinatorial rectangle you'll find in here, and for inequalities it will turn out to be a combinatorial triangle, whatever that means. Okay, so let's look at a linear inequality, right? So a linear inequality will be over x variables and y variables. Okay, larger than some constant a. And now I want to define n. Okay. Now, if we look at an assignment alpha will somehow fix the value of this first sum, and the assignment beta will fix the assignment of the second sum. Okay. So what I'll write alpha of a is just going to be this sum evaluated under alpha. Okay. So a of alpha, it's just going to be the sum of ai times alpha I, right? And similarly, I'll have b of beta to be the sum, like this, the sum of bi beta I. And then, just for convenience, I'll also subtract capital A. Okay. So now this inequality is satisfied by some assignment alpha beta, even only if a of alpha plus b of beta is larger than 0. Okay. So this linear inequality, let's call it L. So L is satisfied if and only if a of alpha plus b of beta is larger than 0. Okay. Ultimately, we'll be interested in when these linear equations are unsatisfied. So I'll just write it in terms of unsat, and I hope you believe me, but if a of alpha plus b of beta is less than 0, then clearly this inequality is unsatisfied under the assignment alpha beta. Okay, and L is unset under alpha beta. Okay, this. Okay. So then I can define the matrix, let's say M sub L, and to be 1, if and only if we have that a of sorry. So we can define the matrix M sub L to be 1, if and only if a of alpha plus b of beta is less than 0 and 0 otherwise. Okay. So what do? We have this matrix which is indexed. missing here, n sub L of alpha beta, okay, which will be 1. So if you look at some entry in this matrix here, right, I'll put a 1 here, if and only if A of alpha plus B of beta is less than 0, or equivalently, even only if L is unsatisfied. Okay. Now, if you think about it, if we order the rows according to the value of B of beta, okay, so let us say that we order the betas so that B, I have B1 here up to B sub n, capital N, I guess, and I order the alphas from alpha 1 here up to alpha sub n, so that I have that beta I is less than beta I plus 1. We have that 9. So that B of beta 1 I is less than B of beta I plus 1. And similarly, we have A of alpha I is less than A of alpha I plus 1. So if we order them according to the value of A and B, then I'm claiming that the ones will form a nice structure. Namely, the ones will form what we call a combinatorial triangle. So under an appropriate ordering, we'll have a combinatorial rectangle, a triangle, with which I mean that if you go from A sub 1 up down to A sub n, then the length of these ones here like decreases. Their monotone decreasing or increasing. And similarly, if we go from here to here. And why can we see this? Well, let's say that A of alpha I, which gives the maximum value, right? So this gives the maximum value for this first term. So then in order to be unsatisfied, less than 0, oh, did I write the wrong way around? Maybe, I don't know. Then B of beta has only very few, I guess I would read the wrong way around. Yeah. But yeah, the point is that once you fix alpha to be very small, I guess, then B of beta has the most room, like it can be the largest. Yeah, I guess. No,
But you said it was fine, no?
I just bottled it. The smallest one is up here. Sorry, the smallest one is up here. If we have here minimum value, then we have maximum value for B of beta to be 1. This means like you have the maximum amount of B of beta, like betas for which you can be unsatisfied, right? And so as you increase A of alpha, like the number of B's that are still causing it to be unsatisfied shrinks slowly. Okay. So okay. So my claim is that if you think a bit about it, a linear inequality will always give you this triangle-like structure. Okay. So meaning that there exists an ordering of the rows and columns so that it looks like a triangle. Okay. But note that it's not really a nice triangle in the sense that it could also look something like this. This would also be a triangle. So all we require is that they're monotone increase. All right. So going forward, we will actually not think of linear inequalities, but we will only think of these triangles. Okay, so we will remain in this space where every linear inequality will somehow be a triangle. Yes.
So informally speaking, we just for every fixed linear inequality, we know that there is some resorting of the columns and rows so that we get this triangle structure.
Exactly. Perfect. Yes. So yeah, so instead of talking about linear inequalities, we'll only talk about this triangle. To be able to do this, we also need to somehow translate the semantic cutting planes proof into whatever the constraint is that we have here. Okay, and this is what I'll do next, and this is called a triangle back. Okay, so let me erase the definition of cutting planes. Yeah, and it's maybe, yeah, once again, it's worth mentioning that that clauses would correspond to combinatorial rectangles. So there is an ordering so that it looks like a rectangle. And then that's a way to talk about resolution. Okay. All right. So before giving you the corresponding definition of cutting planes in this triangle world, let me introduce a game, and this is called the falsified clause search problem. Falsified clause search problem. And this is I'll denote it by search sub phi for some CNF phi. And the search problem lives in the space, lives in 0, 1 to the x times 0, 1 to the y. So just our assignments over x and y variables, and then over the clauses. And remember, n is the number of clauses. And this is a total search problem in the sense that if phi is unsatisfiable and I give you an assignment in alpha beta, then I can always find a clause that is falsified. Okay, so it's a total search problem. And the problem is exactly that I give you like an assignment for the x and y variables, and you're supposed to find a clause that is falsified by this assignment. Okay, so we have the search sub phi problem defined by we have assignment alpha to the x variables, beta to the y variables, and some index I to a clause. So this triplet is in the search problem. Search sub phi if and only if the clause C sub I restricted by alpha union beta is okay. And yeah, it should be clear that if phi is unsat, then this is a total search problem. Search. Wow. So what does this mean? I mean that given alpha beta, there exists an index I or a clause Ci, so that the triplet alpha beta, I guess for all alpha betas there exists an index I, so that all alpha beta I are actually in search sub phi. For all alpha beta there exists an I, so that this triplet is search. But this is clear because for every assignment, by assumption, where phi is unsat, so there is at least one clause that is falsified. Okay. This is very exciting because this problem links TFNP. Look, so that's the theory of total search problems links it with proof complexity, and at the same time we can also link this to communication complexity. Okay, so this is like how this problem lies at the intersection of these three areas and has been the past, I don't know, 10 years or so, like a very active area of research and lots of exciting results that happen. So this problem is like important to remember. It will pop up all over. All right, very good. So in particular, like one thing that I want to point out, and this is some other intuition, is that if we are given a refutation, let's say a reasonable refutation, so like say resolution or so, then we can use this resolution refutation to actually solve this search problem. Okay, why? Well, we know that the initially contradiction, right? We have a refutation is equal to false, right? It's just always false. Okay. Now we have two predecessors. We know that this proof system is sound, I guess. So this means that one of these two. I don't want to say that. Falls under the assignment alpha union beta, right? Sorry. We're given the assignment alpha union beta, and we're supposed to find the falsified clause. So now what can we do? We can look at one of these two predecessors also has to be false under the assignment alpha union beta, right? So what does this mean? Well, we can follow to this falsified clause, And then we can continue going like this, right? Our inductive hypothesis is just that whatever clause we're at, we're always falsifying it. So we continue walking down this proof until we actually get to a clause that is falsified, right? And we'll find this index I, so that alpha beta I is actually in the search problem. All right. So this somehow shows you that as long as you have a consistent proof for that, then you can always solve the search problem with the help of such a refutation. All right. So now what we want to do is we want to characterize semantic cutting planes in this triangle world so that we can solve for the classified search problem using this object, whatever that would look like. Okay. So what is this called? This is called a triangle DAG. So we have a triangle DAG solving the search sub phi problem. Search sub phi problem. So what is this? This is a DAG, so it's a directed acyclic graph. So I can draw it maybe like this, right? I have a DAG, and every node in this DAG is labeled with a triangle. Okay, so let's say this is node U here. Then at node U, I have a triangle T sub U. Okay, and this triangle is over the domain 0, 1 to the x times 0, 1 to the y. Okay. And so, yeah, so what we satisfied, so we have that every node is labeled with a triangle. With a triangle. And so every node, I guess, U is labeled by some TU. From here, 0, 1 to X. Right, 0, 1 to Y. We have that the root is the complete thing. So this corresponds to contradiction. So the root should be false, should falsify every assignment, which means so at the root R, we want that the triangle T sub R is actually equal to the whole space, which is 0, 1 to the X times 0, 1 to the Y. And then we want that that this is a sound proof system. So what does this mean? So soundness implies that for a node U and out children W, we have that the triangle T sub U is contained in the union of the triangle T sub V union T sub W. This really is just corresponding to soundness, like from normal proof systems. And yeah, so I'm assuming that the DAG has out degree at most. And finally, every leaf of this DAG is labeled by some clause. So every leaf is labeled by a clause C sub I or I in M. So a clause in the formula. Okay. So that for all assignments, alpha beta in the every leaf U is labeled by a clause such that all assignments in the triangle, so whatever this node rules out, T sub U, for all assignments that this node rules out, it holds that alpha beta, like the clause CI under alpha beta evaluates to false. Okay. What is this saying? This is just saying that at the leaf we have for at least every node satisfies that all assignments ruled out by this node also have to falsify this clause that it is labeled. Okay. All right.
And the root is everything also. Right?
Yeah, that's here.
That's real. Okay.
The root is everything. We have consistency, which corresponds to T mu being containing TV union TW. And yeah, we have the labeling of the leaves. Okay. And now the claim is that there is a semantic hiding place refutation of some formula phi, even only if there is a triangle DAG solving the search phi problem of the same size. Okay. Hope you remember search problem. So what do we have? We have the theorem that states that there is a triangle DAG for search phi of size S, even only there is a semantic cutting planes refutation of phi in size S. Okay. I'll not prove this. Should be quite immediate by the discussion that we had. Like so, right? Every inequality you can translate to a triangle and vice versa, and yeah, the size just remains the same because for each inequality you have a triangle, vice versa. Okay, and yeah, and like yeah, whatever else. All right, good. So for the rest of the proof, we'll forget cutting planes. We'll just think about these triangle DAGs and solving this search phi problem. And we have now like set up everything so that I actually can start with the proof. Like up to here was just like trying to massage the problem into a form so that I can actually work with it. Okay. All right. So we have this triangle then, and we want to do a bottleneck accounting argument. So what does this mean? So proof starts, right? So finite proof starts of that here. All right. So suppose we're given a small. So suppose we're given a triangle DAG pi. What do we want to construct? So let me just draw pi. We have pi here. What we want to construct is we want to construct a mapping mu, mapping assignments from 0, 1 to the x and 0, 1 to the y. So we have 0, 1 to the x union 0, 1 to the y. So all these partial assignments to the x variables and y variables are going to be mapped into the vertices of this triangle. Okay? And in fact, it's going to be a partial map. So not everything will be mapped. Just some assignments will be mapped. Okay? And we do it in such a way that the inverse, the size of the inverse of any node u is going to be small. So the number of assignments mapped to a single node u in our triangle DAG, it's going to be very few. Okay, so I wrote down some numbers. So it's at most 2 to the n minus w times k over 4. I'll tell you in a second what the parameter w is. Remember that k is from k-CNF, like the size of our clauses that we sample. And in addition, we have the size of the domain of mu. So the number of assignments mapped to a node in pi, it's going to be very large. And it's going to be of size at least 2 to the n minus 1. Okay. If we have this statement that few assignments are mapped to a single node, And we have that the number of assignments mapped is of size 2 to the n minus 1, then we know that the size of I has to be at least 2 to the n minus 1 divided by this number, right? 2 to the n minus wk over 4. So we know that the lower bound will be something like 2 to the w times k over 4. Okay, maybe there's a 1 somewhere, maybe minus 1. Okay. So this will be our plan for the remaining time to construct a mu satisfying these two conditions, that it maps not too many assignments to a single node, but it maps almost a large fraction, at least half of assignments. All right. You think of W so that we can actually get the theorem. So W is going to be it can be set to something the minimum of 2 to the k over 4 minus 1 or minus 1 exponent and c times n, where this is the expansion guarantee. So this is this parameter here, and yeah, W cannot be larger than 2 to the k. Okay. All right. Any questions? I think here's a natural point to take a break. Let's take a 10-minute break and reconvene.
So just to say, I mean, one thing, if we want to map back the very first lower bound that we did for the pigeonhole principle formula, for then you could, instead of looking at the triangle DAG, we could have looked at the resolution DAG, and mu was a complete mapping, and then we kind of had the same or similar parameters. But we're going to have to work, like it's going to be much more complicated for cutting planes. In particular, for some mysterious reason that we will see, we cannot quite map all assignments. Any other questions, comments?
All right. Just 2-second recap. We went from semantic cutting planes to triangle DAGs, where we have DAGs labeled by triangles, and we want to solve this falsified clause search problem. We want to prove that any such DAG has to be large for random CNFs. And our plan is going to be that we're going to create some partial map mu from assignments from 0, 1 to the x and 0, 1 to the y to the vertices of our proof, so that every node is mapped to a few assignments are mapped to a single node, but enough are mapped to so that we can argue that the size of the refutation is large. All right. I'll erase the definition of a triangle DAG. Yeah. I'll remind you if you need the definitions. All right. So how are we going to construct this map mu? So first, maybe I should explain this mysterious parameter W that I left here. So let us consider an assignment, some assignment gamma in 0, 1 to the x union 0, 1 to the y. Okay. So we have a partial assignment with the x and the y variables. And for a given node, u in our refutation phi, I want to define a width measure. And this width measure is somehow going to assign a width at this node for an assignment gamma. And let me just define it formally first, and I'll explain to you in a second what it's saying. So it's going to look at the set S of axioms. In fact, it's going to look at the minimum size of any such S, so that the union of the triangles of the clauses C sub I covers the line gamma in the triangle at U. So it covers the line gamma in the triangle U. Okay. Let me draw a picture. So we are at U, right? So this means U is associated with a triangle. Whatever this may look like, right? This is our triangle T sub U. And we're given some gamma. It's either a row or a column. Let's say it's a row. So we have gamma here. So we're looking at this slice of the triangle here. This slice here, this is this guy. This is TU, like somehow at gamma. Okay. And now what we're looking for is we're looking for a minimum subset of axioms so that the triangles corresponding to these axioms actually cover this entire line. So right, we are in this space, and we know that an axiom somehow rules out some assignments. And they're actually going to be rectangles because we're talking about clauses, but whatever, they have some shape, right? Turns out to be rectangles. And we're looking at the minimum set of S so that we can cover this line with these axioms. Okay. This is a width measure. Oddly enough, it's not a width measure for the node U itself, but it's a width measure for the node U and a partial assignment gamma, which is a bit odd. But for intuition, in case of resolution, we just had the width of U being the minimum number of axioms that imply a clause, right? So for intuition, in resolution, like in Bensas and Biggerson, what are you looking for? You're looking for like somehow the minimum number of axioms that imply the clause. Okay. So in resolution, we just looked at the minimum number of axioms that imply the clause, which in this triangle setting would just mean that you're looking for a covering of the entire triangle by axioms. Okay. But what we're somehow doing, which is very counterintuitive, is that we're going to look at the node U and the partial assignment gamma, and we're going to look at the minimum covering of this slice of the triangle. A bit of funny definition. A bit different from resolution. All right. And so now what we're going to do, we're going to define mu by somehow defining a threshold for this width measure. And whenever we find, so we're going to traverse our proof pi in a topological order. So we're going to like start with the leaves, and then we're going to move up the proof slowly. And we're going to assign an assignment to a node if it is above the threshold for the first time. Okay, that's somehow going to be our assignment. I'll make it more formal in a second. Okay.
Do you have exactly the same definition for columns also, and you're going to look at both?
Yeah,
or?
yeah. So this is defined for gamma. Gamma can be either a row or a column.
Okay.
Okay. I mean, yeah. So just make it very clear. All our triangles, like all the triangles T, they live in 0, 1 to the x times 0, 1 to. Okay. All right. Now, it shouldn't be so hard to see that if we look at the node U and its predecessors V1, or its out neighbors V1 and V2 in our proof pi, then I'm claiming that the width at gamma of V1 plus the width of gamma at V2 is a bound on the width at U. Okay. So what am I claiming? I claim that in this setting, we have that the width of U gamma is bounded by the width of V1 gamma plus the width of V2 gamma. Okay. Why is this so? Well, we are at U. Our triangle definition says that the triangles at V1 and V2 need to cover TU. Okay. So let me draw maybe covering of this triangle, right? When we cover this triangle, let's say this is TV1 and this is TV2. Now, what am I saying? I'm saying the width at V1 of gamma, so this is a covering of this part of the line, plus a covering of the triangle V2 at gamma. So we have a covering of this part of the line. This is an upper bound of the cover size of the whole TU triangle, right? And this should be immediate in the sense that you can take the covering from here, union the covering from here, and this is going to cover the whole line, just by definition. All right. Prove the first property. That's cool. So somehow this measure is subadditive in the second, in the first problem. Let me not say it. All right. Okay, so now I can tell you how to define the measure. I think I'll now erase the rightmost board. So we define mu as follows. We consider the nodes of the proof in topological order. So we have U1 blah, 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 up to U size of pi. In pi sorted topological. I mean, what I mean is that any out neighbor comes before the node itself. Okay?
So the root is last?
The root is last.
Okay.
For alpha in 0, 1 to the x, we do the following. If the width at u of alpha we are larger than our threshold w, then we do the following. We map the measure of alpha, we map alpha to u, and then we remove alpha from all following triangles. Okay? So erase the alpha line from all other triangles.
Did you say what happens if alpha isn't even covered by? And we just define the width to be 0, or?
What if alpha is not in the triangle, if it's out here?
Yeah.
But then 0, right?
Okay.
The minimum set that covers the line, which is empty, is 0.
Okay.
Minimum set size is 0.
Okay.
I think that's fine. So, okay, so we consider U1 to U pi sorted topologically, meaning that the root comes last. Then for every assignment to the x variables, what we do is we look at the node u that we're currently looking at, right? If alpha is large, like has larger width than w at this one node, then we set alpha to, we map alpha to this node, and then we erase the alpha line from all future triangles. Okay, it's just gone. And we do the same for beta in 0, 1 to the y. Do the same. Okay. Questions?
What are mu mappings? Is it mapping alpha cross betas or alphas and betas separately?
It's a union.
It's a union. Okay, so
union.
separately.
It's separate.
Okay, good.
It maps alphas and betas.
Perfect.
Okay, like from, yeah. Okay, any questions? So sort the nodes topologically. The first time you find alpha to be larger than w in any node, assign it. Okay. All right. Let's do a simple claim. Claim. holds that W U gamma is at most W after the alpha. Sorry, before alpha. For all assignments gamma that still live, that still exist, it might be that we have erased them before. Then they're gone. That's fine. But for anything that remains, it holds that the width at the node that we're currently looking at, the gamma is at most 2W. Okay? And this simply follows by this claim, because we know that in all previous nodes, we had at most W, right? Because otherwise we would have assigned it there. So this means that certainly at the node that we're currently considering, we have width at most 2W. Okay.
What does it mean to erase the alpha? This, if alpha is a row, then this is going to affect the column measures for later triangles?
The column measure may drop. Very good. So the column measure or the row measure may drop throughout this process, but it will never increase because we just erase lines. As we erase lines, the measure may shrink, but nothing bad will happen.
Okay, and this is important for us for some reason that we will see.
Yes. Okay. And we also know that after running the algo, we have that the width of U gamma is at most W. I guess I should have proven this one before this one. But whatever. Just like so we remember. Okay. If it would be larger than W, we would have assigned it. All that could have happened is that we erased some lines, but that would just drop the measure. Okay.
Sorry, I guess I just have one question.
Yes.
So here, I guess you have an outer loop for the U's.
Yeah.
Yeah, okay, yeah, okay, yeah.
Yeah, this you have a UI here, and you do them in this order.
Okay, cool, thanks.
Yeah, you have an outer loop on the U's.
So we're going to walk over the triangle-like nodes in order. For every node in the triangle, we go over all remaining assignments and see if we want to do anything with them. Then we're done. We do the cleaning. We move on.
Yeah. Okay. What remains to do? Well, it remains to show these two statements, right? It remains to argue that.
Okay, but then technically, when you say from all other triangles, that means from not the guy we're at in now, but for all later guys, because now we're going to process all the assignments in one go for this triangle that we're looking at right now, and the cleaning you only do at later.
No, I just erase it.
Yeah, from later nodes.
No, all nodes, everything. But it's not so important.
It's not so important because then you start wondering whether they're sequencing, like in which order you're dealing with the alphas could.
It doesn't matter.
It doesn't matter. Okay.
And I mean the width of the alphas doesn't matter, right? Like the width of a row is defined independently of another row.
Yes, but what if you start interleaving rows and columns? Oh, you don't.
We first do the rows.
First process all the rows.
And then the columns.
Okay, good.
So concrete, I think you can mix them in any order if you want. If you feel better doing first half of alphas, half betas, and alphas again and betas, this will also work.
I would feel worse. But
Okay,
you're
you
saying
need
it.
to.
But you're saying
We
even
understand
that
each
would
other.
work.
Good. Yeah, you can just do the mix.
Or I would feel more nervous.
All right. Okay, so we need to prove these two things here. I'll call this statement 1 and this statement 2. Okay. All right, we'll start with statement 1. That's the boring one. Statement 2 is more interesting. But we're almost home. There's not much left to be done. These are all the definitions, and now you just need to do some arguments. Okay. So claim 1. lemma 1. We're saying that the size of the domain of mu is at least 1/2 times 2 to the n. Okay, contradiction, proof by contradiction. Let us assume that the size of the domain of mu is less than 1/2.
Sorry, could you remind us, x and y, do they have n variables each or n half variables
They have
each? Or
n variables.
n variables?
Yes, yes. Yeah, they have n variables. Okay. Yeah, very good. Then it's not written anywhere.
So I can actually fail to map like pretty much all of the betas and half of the alphas.
Yeah.
But it won't be worse than that.
Yeah.
Okay. But we're looking at a significant loss, but not too bad.
Okay. I'll erase this here. So let's look at mu. No, let's look at fix the root R. Okay, we look at the root of our protocol after running this whole procedure. Okay, after defining mu. So we're left with at root, we're left with a triangle, which is actually a rectangle, which is equal to simply a set A sub r times a set B sub r, where A sub r is contained in 0, 1 to the x, and B sub r is contained in 0, 1 to the y. Okay, we're left with a rectangle at the root, and somehow we want to argue that these two sets are small. Okay. But because of contradiction, we can assume that the size of AR and BR is at least, what am I writing here? 2 to the n minus 1. If this is not entirely true, it's probably 2 to the n minus 2. Okay. Whatever we're left with in the end are the assigned, because, right, we erased all the ones that we mapped to somewhere. So we're only left with assignments that are not mapped to anything in the tree. Okay, or in the DAG. So this means that both these sets need to be fairly large in order to have the domain is small. Okay. I'm thinking I might want to change this statement. State this as minimum feel like it. I'm a bit confused. Like I can only conclude from this assumption, I can only conclude that one of these is larger than 2 to the n minus 2.
No, but you want both, right? And I think you can get both.
Yeah, I'm confused.
Well, I mean,
One might be very small and the other one might be huge, right?
yeah, but if one of them is very small, I mean, the argument you want to say, if one of them is really, really small, then you're already happy, then you mapped enough.
Oh, very good. Yeah.
And I think those numbers maybe work out that you have now, possibly. Or else some minor adjustment will give it, no?
Yeah, I think I can even do 2 to the n minus 1. Like if one of them has this size, then we're certainly done. So then we can certainly assume that both of them are not. Yes, thank you for fixing that. This part of my head. All right, so we're left with this rectangle. And now what we want to say is that, well, we know that, so for alpha in AR, we know that the width at the root R of alpha is bounded by W, right? If this were not the case, we would have assigned it to the root. Okay, good. Now I want to use the fact that I know that there is a set of at most. So, okay, so what does this look like? So what am I saying? I fix some alpha here, and I'm looking at this line, and I know that there are at most W axioms that cover this line. This means that every assignment beta here has to falsify one of these clauses. These are few clauses, which means there are few assignments in B sub R. Okay? You only have the most W clauses, so we'll be able to argue that only few assignments actually falsify one of these W clauses. Let us do this more careful. Right, so for every point, so for any assignment beta in B sub R, we know that it does not satisfy one clause of a set S of size was W. Okay, so we have a set S of clauses, so that every beta can, at least one of them, it cannot satisfy. Okay. All right. So let's look at sampling beta uniform and random. And let's look at the probability that beta is in B sub R. Okay. Well, I can bound this by the probability that beta does not satisfy a clause C in S, right? This is at most the probability that beta does not satisfy a clause C in S. Do unibound, I guess, is at most the sum of C in S of the probability of the max probability over C in S. Let's write this size of S times the max probability that beta does not satisfy C. And we know that this is equal to, well, S is at most size of W, and probability that beta does not satisfy for C is the same for all C, namely it's 2 to the minus k. Because all the bits need to be, the variables need to be set. Okay. What does this mean? This means that our set size of B sub R is bounded by W times 2 to the minus k times 2 to the size of Y, which is at most less than 2 to the n minus 1, assuming that k 2 to the k blah, blah, W is less than 2 to the k plus 1. Okay, so yeah, what did we say? We said that, well, every assignment beta in B sub R needs to falsify or not, does not satisfy one thing, one clause in the set S, the set S is small, the probability of not satisfying one of these clauses is 2 to the minus k. So we, yeah. Okay, there are very few such assignments. Good enough? Great, let's move on. The more fun part.
So basically what happened, you said you looked at A and then you figured out that B was too small, but it can't be, and now we have a contradiction.
Yes.
Sorry, I was...
Yeah, I didn't say that. Yeah. So what was our conclusion? My conclusion was that B sub r is less than 2 to the n minus 1, but we assumed that it's larger, so contradiction.
Just first assume that AR is small, then we're done. Otherwise, BR is small.
What?
But first, we would assume that AR is small, then we are done. Otherwise, yes, you're assuming BR.
You can just do the same argument for yourself.
Yeah.
You use very little. I mean, I guess you're using that there exists at least one assignment. If there doesn't exist an assignment in your set, you don't. I mean, yes,
Just if you really need to assume that BR was larger than 2 does it need to be a contradiction argument? Just to derive that BR is small at the end. Just the rest of that.
I mean, sure, there are different ways of stating it.
Basically, what you're saying is that if I fail to map an alpha, then capital B is small. Is that what we proved?
Yeah, if there exists an alpha, then capital B is small. Yes. Yeah. So either there exists no alpha, in which case we're done, or very good. Yeah, very good. All right, that was pretty boring. We didn't even use expansion of the underlying graph. Right? We used nothing. Just used, like, we did use the fact that somehow k is logarithmic. We are using it. Because we want to choose W to be like n over k. Because I'm sure you all remember, we get an exponential lower bound in W times k. Okay. Very good. So let's move on. The more fun part is lemma 2, where we prove that we don't map too many assignments to a fixed node.
I guess I'm a bit confused whether, do we really, I mean, does this process actually fail to map alphas and betas, or is it just that this is good enough for us? Still looks a little bit like, I don't understand whether we really fail to map alphas and betas, or we just don't know. Could it be that we actually map all of them if we worked a bit harder, and this is, we don't need to work harder?
I have no idea. I never thought about it. I have no idea.
But it's good enough. I mean,
Could you just +1?
yeah, no. I just...
Okay. The more fun is the second part. Namely, we want to show that for all u in the vertices of pi, it holds that the size, like the number of things mapped to this one vertex, is bounded by something like 2 to the n minus divided numbers. WK. Okay. Okay, so we want to argue that there are not too many assignments mapped to a single node. Now, let us consider consider u before. So consider u before running the algorithm on it. And what I mean by the algorithm, it's just how we define mu. Okay? So we look at mu before we run the algorithm. All right, so what do we know? We know that for all beta, we know that the width at the node u of an assignment beta is bounded by 2w. Okay. And we want to use this fact to argue that there are not too many alphas, so you want to use this fact to argue that there are not too many, that there are not too many alpha such that the width at u of alpha is larger than w. Okay? If we can do this, then we're done. And we can do the same argument symmetrically on beta. Okay? So you want to use the fact that we know that every line has kind of bounded width to say that there are not too many lines, like, yeah, this column against line. Okay? All right. And what are we going to do? We're going to build a candidate covering of all the lines of alpha. But this is going to fail. Sometimes we're going to analyze when we fail. Okay? All right. So what does this look like? So we have our triangle. And we're looking at some line beta. And I said that this line has a covering of 2w accent, right? May look something like this. Okay, so this line here can be covered by 2w many axioms. Now we want to argue that there are few assignments alpha that require more than w many axioms to cover it. Okay, what are we going to do? We're going to use the knowledge of these coverings recursively to argue. So what are we going to do? So we're going to split this triangle according to the first covering. Okay, split it something like this. And now we're going to recursively do the same again. We're going to look at, like in this first remaining triangle up here, maybe I should use colors, like better. We're going to look at in this remaining triangle here, and we're going to look at the first assignment beta prime, and we again know that we can cover it with 2w many axioms. Something like this.
Sorry, they're overlapping, right? So how do you deal
Don't
with
worry
that?
about this. Just let it overlap. I'll get to it just in a second.
I'm just trying to understand your picture, so I'm getting it.
Yeah, they are overlapping. Let's ignore this for now.
Okay.
It's not important. So what we're going to do is we're going to try to cover this line alpha by like recursively finding new assignments and using like another 2w to cover all the assignments. And we're going to do this recursively until we hit that w. And at that point, we have to stop. Because then we tried to do our best. We tried to find a covering. And now we want to say that there are not many assignments that fail this candidate covering. Maybe this was a bit quick, and that's okay.
It was, but you're saying in the next step, you're going to just look inside the green guy.
Yes, I'll do it formally now. Okay. So let's call this covering for beta as this is diffs in the set of axioms, so in M. Okay. So this S covers the beta line of this triangle. So we know that every alpha is covered by S. So, I mean, what do I mean by this? I mean that all alpha, it holds that there exists an I in S, so that the clause Ci restricted by alpha is false. Okay. And here I'm only looking at all the alphas that actually live in this triangle. I don't care about the other side. Okay. So every alpha is covered by S. So what does this mean? I can look at the original triangle T sub u that we're currently looking at. And then I'll draw edges. And this is going to be size of S many. And I'll have rectangles. So let's call these R1 here, R2, and so on. So these are the rectangles in S or corresponding to axioms. So we have R1, R2, and so on. And then our size of S here, right? These are the rectangles in the covering of this one line, the axioms. And then we're going to get to new nodes, and these are going to be the remaining things. So this is going to be the remaining triangles. So this is T sub 1, this is T sub 2, and so on.
And this construction depends on your choice of beta, but I guess it's like completely arbitrary. Well, you pick the first beta you can think of? Or?
I want to sort them and then pick the largest.
Oh, you
I'm
picked
sure
this.
that I cover everything.
Oh, okay. This is what you said.
Yes.
Okay.
I did not say that.
Okay.
I did absolutely not. No. You want to sort them and pick the largest one so that you cover every alpha. If you pick one out here, it will be a bit annoying because you don't cover many of the alphas.
Okay, so now we're actually starting to use combinatorial triangle.
Yes.
Thank you.
And now, so Jakob asked me before what these triangles are, and you should really think of them as you just take the rectangle here, and you take the intersection of these rows with this triangle. Really just the remainder here in this triangle. And these triangles may overlap if they overlapped before. But like if these two rectangles overlap, then the remaining triangles overlap. This is not a problem. It's just hurting us in the bounds, but it doesn't. Okay, so far so good. Okay, so let me repeat. So what do? We look at beta, look at the covering. We split according to in what rectangle alpha lives in. We create this tree and we recurse on every remaining triangle. And we do this up to depth k, up to depth w. Up to depth w. Okay. What does this mean? So we have we do this recursively up to depth w. What does this mean? If some leaf here ends somewhere, what does this mean? This means that, well, at some point the recursion stopped, meaning that all the assignments were covered that would end up in this leaf. And it's covered by at most w many things. So any assignment ending in a leaf high up, we're fine. We can cover it here. So the only ones that we worry about are really the assignments that end up at leaves at depth w. Okay, and then right, yeah.
How did we? Sorry, I'm just trying to see how do we pick the second beta? Sorry.
You just recursively, like as I did this up here, and you're saying here. But like I will have like a triangle here, right? So I have this green triangle. I look at the first assignment, like it's going to be an orange triangle. So this triangle will look something like this, right? Maybe. I'm going to look again at the first beta here, and I'm going to do the same. So same procedure. Okay. I'm going to pick a covering for beta. I know it's of width. It's bounded by 2w. So, right, the out degree of every node is equals to 2w, and we can do what it is. Okay. An assignment alpha will fall onto a branch, right? Because every time I have all the assignments that are in this rectangle, and I don't partition it, but it will end up in at least one of these children. Okay. So this means that I can follow a branch with a given assignment and see where the assignments end up. If they end up in a leaf that is of depth less than w, then I know that we can cover this entire line with less than w many rectangles, and we can rule out that these assignments will be assigned to you, right? All right, so all we worry about are how many assignments may end up at depth w. Those we don't really know. Those are the ones that might have width and u of larger than w. Okay. So how many paths do we have up to depth W. Should be easy. Yeah, 2W to the W. We have at most this many paths down to a single node, because every time we branch out with 2W many possibilities. And so this means that any assignment that ends up in a fixed leaf has to not satisfy all the axioms on its way. Okay? If it would satisfy them, it could not be in its rectangle. So what does this mean? This means that the number of assignments that may end up in a single leaf is something bounded by 2 to the n minus the size of the neighborhood of, let's write this calligraphic R, where these rectangles are really, where calligraphic R is just the set R1, R2, so on. I mean, like, not the ones going here to the right, but the ones going down here on the branch, the line on the branch. These correspond to, like, every assignment that ends up in a leaf must not satisfy any of these axioms. Okay, this means that all, if you look at the graph, if you look at the, so right, this is now a set R of axioms, and we can look at the neighborhood of R in the variables, that we call incidence graph. Then we know that all these variables need to be fixed to one particular value, because if they're not fixed to a unique value, so that all these clauses are falsified or not satisfied, we would not end up in this leaf. Okay? So in particular, the number of assignments that may end up in this one leaf is bounded by 2 to the n, because that's 2 to the n is the arity of x, minus the neighborhood of this set calligraphic R. Okay? And now we can use expansion to argue that this is bounded by 2 to the n minus size of s times k over 2. This is why I left this barely visible lemma here. We assume that we have k over 2 expansion, right? So we have, why did I write s? We have calligraphic R times k over 2. Okay? And this is equal to 2 to the n times n minus a w. Okay. Now we know that the size of R, because we are at depth w, is W. All right, great. So we bounded the number of assignments that may end up in a single leaf. Okay. Now all that remains is to like multiply this by the number of leaves we have. So what do we get? We get something like 2 to the n minus kw over 2 minus w log 2w. Guess I can take the w outside. So I get something like n 2 to the n minus w times k over 2 minus log 2w. Okay. Now if I assume that log 2w is bounded by k over 4, then I really get what I want, right? So I can say that this is bounded by 2 to the n minus w k over 4. Here I'm assuming that, do we write this cleanly? We write that 2w is bounded by 2k. Okay. And this finishes. All right. I was urged to end with some open problems.
Sorry, you lost me in this group.
Yeah, I noticed.
Yeah, no. So it's probably something very, very basic, but I still don't understand the recursive construction. So,
All right.
Because.
So what do we do? So we are given a rectangle, a triangle, sorry.
Yeah.
We're given a triangle.
So, and yes.
And we fix this column beta,
Which is the largest
one. Okay. And we know from our construction that the width is bounded at u of beta, whatever, yeah. So we know that there exists a covering, let's call this, of rectangles or of axioms of this line. Okay, very good. Something like this. And so we know that every alpha needs to be in one of these rectangles.
Absolutely.
Great. So now let's take all the alphas from here and I'll assign them to these children depending on whether alpha is in Ri or not. I can do this. Good. So in particular, I'll assign to for R1, I'll assign these alphas. For R2, I'll assign these alphas. Okay. Once I've assigned alphas, I can look at what is the triangle induced by these colorful bars in the what is the induced triangle of the triangle by this green thing. What I mean by this, I can look at the remaining triangle. This would be the green guy, and then I can look at the orange guy. It looks something like this. Okay.
Yeah.
Okay. So now I want to remove Ri, whatever. So now I can recurse, right? So now I have the green triangle here, and I have the orange triangle here. I can continue applying the same procedure.
Could you please elaborate? Because now it's like, what's if I pick in particular, beta is still the largest beta.
No, it's outside. I have explicitly drawn the orange parts to only include the columns that are not contained in R2.
Thank you. So R1 and R2 are rectangles of different, but they don't extend too far into the.
We don't know. They are combinatorial, so they might not look so nice. They might be scattered through, right, through the whole thing.
Yeah, yeah.
So it doesn't look as nice as I draw it here. But still, I can look at the columns that fall into this rectangle R2, and I can look at the remaining part of the rectangle that is not covered by R2.
Okay. And I missed the part where you removed all of the rectangle also, like in the beta space.
Very good. Okay, I bet. So, okay, very good. So then we recurse, right? Now beta is certainly covered, so now it's a different beta where we take the covering.
Absolutely, yeah.
And now we can recurse. If an assignment ends up in a leaf less than depth W, then we know that all the line is covered by less than W many rectangles, right?
And hence it is not time to map that beta today, and
Exactly.
that alpha today.
Exactly. So we're only looking at the one at depth W. There are at most 2W to W many. By expansion, we know that, or no, not by expansion, but we know that.
So could you, please do that part of the argument also carefully,
Okay,
because you lost me by now.
We know that we have these axioms on the path.
Mhm.
We know that we cannot satisfy these axioms. If we would satisfy them, we certainly cannot be in the answer set, right?
Mhm.
We have to falsify all these axioms. Let's say this is his R set.
Mhm.
If we cannot satisfy these, this means that we have to set these to the unique assignment so that we do not satisfy these clauses. Let's look at how many variables we have here. We have neighborhood of R many, okay? So how many assignments may there be? Well, outside the neighborhood, I have no control. The assignment may be any. So we have 2 to the n minus size of the neighborhood many assignments that may falsify this set R. Okay? But now we can use expansion to argue that the neighborhood of R is very large, and because it's so large, we're very happy. Okay? So it's like 2 to the n minus kW over 2. All right, very good. Now putting everything together, we have to multiply the number of assignments in a particular leaf times the number of leaves. So we get something like 2W to the W times 2 to the n minus kW over 2. You can simplify this to 2 to the n minus W times k over 2 minus log of 2W. And then assuming that W is not too large, exponential in K, we get our bound.
Basically, if I ignore all your calculations, let's just see if I can get this right. So we're thinking about what property does an alpha have that when we reach node U, this is alpha's time. Now alpha is going to be mapped. And you're saying such an alpha will in particular have the property that it is not satisfying a somewhat large subset of clauses of the formula. Okay, so any alpha that gets mapped at this node does not satisfy a somewhat large subset of axioms.
Yeah.
Now, by expansion,
And because we're looking at clauses,
right. By expansion, and since we're looking at clauses, this now means that we're actually fixing a fairly large subset of variables that we don't have any wiggle room for. So this is somehow this property of bottleneck counting over clauses comes in through the back door. No? Somehow, I mean, this is a magic argument.
okay. So, yeah, so, okay. So one thing I have not mentioned is that if you would instead of sampling clauses, if you would sample XORs, random K XORs, then we know that this is actually quasi-poly easy for cutting plans. So this lower bound can certainly not apply for random K XOR. And where we see this, why this does not apply for random K XOR is exactly here, because here we are saying because we have a clause, we have very few assignments that would satisfy the clause. Namely, there would, well, the other way around. There are very few assignments that would not satisfy a clause. Okay, almost false back. Then maybe just one. And this allows us to do this step. It like allows us to say, well, because we have so good expansion, all these variables basically need to be fixed to a unique value, right? But if we have XORs, well, they're very much not fixed. We only require one bit for every clause to be fixed. So then you cannot do this argument. And so in my mind, the most important open problem at this point is to try to prove the same thing, but for balanced predicates. So for predicates that have about the same number of accepting as rejecting inputs, try to prove that sampling these randomly is still hard for cutting plans. And one example predicate would be product or maybe majority. Not sure about majority, but I think product.
Where in this argument, one other question, where are we using that K is logarithmic?
Yeah, also here.
Because so saying this is one place, I guess, where it's nice to have K logarithmic is so in this cleanup step which you didn't even argue about.
So W should be large. We want to prove an exponential in W times K lower bound. So W should be something like polynomial in N. But this means that log W will be something like log N. And I need this K to be larger. Because if this K is smaller than log N, I'm dead.
Okay, so even if I say I commit to sampling a 100 CNF with 50 variables from the X set and 50 variables from the Y set, this is where you would die. We have no idea how to do this.
Yes, yes. Yeah, so the constant K is also an open problem. In my mind, I think it's more important to try to do the balanced predicates. Because there we actually would have maybe possibly nice applications for the truth table topology. But yeah. But of course, it would be aesthetically pleasing if we could get K-counts.
And so again, where did we get the log from?
Is log 2?
Yeah.
From the W to W. So this is where now you have to maybe correct me, Wittmeyer and Beam, or Beam and Wittmeyer. Are these correct names? So they did the same argument for the pigeonhole principle and for the functional pigeonhole principle. That's correct.
Bitwise.
Binary. Sorry, yeah, binary. Yeah. Binary pigeonhole
I
principle.
think for the standard pigeonhole principle, I would be a little bit worried.
Yeah. So, but there they need to reduce this count, and they do this by a clever argument on this. Let me not say.
Okay, so you're saying this bottleneck counting thingy has been done for binary pigeonhole principle also.
Yeah, and also binary click. Yeah, hey, it's yours. Okay.
Okay, 2 to the W, and this was because we were summing over, this was the number of leaves. Okay, so suppose we're happy with the proof, but you already, during the proof discussion, you moved over to open problems, or you discussed the open problems already now, or?
I think so. So balanced predicates and the k-CNF, like for constant k. I don't have any other problems. Maybe I don't have through them more.
But you somehow need, okay, so the reason you can do this for k-CNF, is it conceivable that regardless of which formula you're looking at, that you will able, I mean, you're somehow magically doing a partition of the variables for a formula where there is no partition. I mean, for our clique coloring formulas, this is kind of clear where we have the clique part and we have the coloring part. For random k-CNFs and for the bitwise pigeonhole principle, it's not entirely, well, for the bitwise pigeonhole principle, I guess they take half of the bits each. Here you somehow impose a partition and do some cleanup. Do you envision, do we envision that for any formula we want to prove a lower bound for, I mean, that there would be such a partition of the variables? Because I guess otherwise it would also be like a, say we want, okay, we believe that coloring is hard, right? Probably 0-1 interlinear programming doesn't solve coloring. So suppose we want the coloring lower bound. Would we expect to be able to somehow partition the variables somehow, or are we looking for, or could we go beyond and prove like lower bounds when we actually just have a single set of variables that we cannot partition?
I mean, so maybe you can prove it for, I suspect you could prove it for the binary encoding, where you can split the colors, like the knowledge of one color between two players.
Yeah.
Then you can probably get coloring lower bounds, I suspect.
Good. I would prefer unobfuscated lower bounds.
Yeah, then we don't know. Obfuscate.
Even this is not, if you do this.
Yeah, it's not obvious.
More questions or comments? I guess let's thank Kilian for today's lecture.